Now let's tackle a problem involving ideal gas flowing through a pipe. And we have to be given a bunch of inflow conditions, and then we'll be able to compute some of the outflow conditions. So imagine that we're told that we have a steady flow with the following parameters: this inflow density, this inflow pressure, this inflow temperature, an inflow radius, so this is the radius of the pipe at the inflow point, and an inflow velocity. So we have all of that information. Now, that's actually not enough, because we have the freedom to do a few things with the outflow at this point. So let's say that we're further told we don't know the exit density and we don't know the exit pressure. But we do know things like the exit temperature, the exit radius, so the size of the pipe on its way out, and the exit velocity. So we're given some of the information for the exit conditions, but not all of them. The picture you should have in mind for this problem is that of a nozzle. So we start with a larger radius than we exit with. That means it has to have the shape of a nozzle. For an incompressible flow, this is a pretty simple problem, but actually if it's an ideal gas flow, generally speaking, we would assume that probably the gas can be compressed, so we'll need to figure out what the density is and what the pressure are at the exit point. So let's do that. Okay, so we'll start with conservation of mass in an open system. dm dt equals the difference between m dots. And we know that this has to be 0 in this case because I said it's steady flow. So dm dt equals 0 for steady flow. That tells us immediately that m dot I must equal m dot E. And remember, the m dot values are measured at the inlet and at the exit respectively. So the two parts that I have labeled on that nozzle, that's where the m dots are measured. Well, we can substitute in the general expression for m dot, namely that m dot is rho a times the velocity. So rho AV, remember V has ears, it's velocity in this context. And we have a subscript I for inlet on the left-hand side, and then E for exit on the right-hand side. This is already enough information to solve for the exit density. So let's solve for rho sub E. All right, we rearrange rho sub E equals rho sub I times the ratio of the area for the inlet to the area of the exit times now the velocity of the inlet divided by the velocity of the exit. So you need to keep track of your subscripts here when you do this. The area of the pipe, in either case, is pi r squared, even though we have to subscript r because the radii are different at the inlet and exit. So let's put that in. A equals pi r squared. That tells us that our expression for the density becomes this. Now the factors of pi will cancel, so really we'll just substitute in for the area ratio a ratio of the radii squared. We'll move this up and simplify this a little bit by canceling the pi factor. Okay, now we're to the point where we can put in numbers. We know all of the stuff on the right-hand side, so let's do that. Okay, density is 1.23 for the inlet. The ratio of radii is 20 to 5, and then that quantity is squared. The ratio of velocities is 100 to 207. All right, so we do that, and we get an exit density of 9.5 kilograms per cubic meter. Okay, obviously this must have been a compressible system, right? Because that's very different from 1.23. We know that we're not dealing with water in this case. Water, also not a very good ideal gas for exactly that reason. Okay, so let's substitute in that value for the exit density. There, we have it over there now. Now we can figure out the exit pressure. Well, how do we do that? Well, you just need to remember that this is an ideal gas. So actually we have enough information between the temperature and density that we can figure out what the pressure must be. Let me show you. So generally speaking, for an ideal gas, we know that P little v equals RT. Remember that little v is the specific volume, so we can put a ratio of PV over T on both sides, right? That has to be true for a single gas. We're not changing R, so it must be true that the inlet PV over T must equal the exit PV over T. Let's get rid of the specific volume because I don't want to confuse that with velocity. The nice thing is specific volume is the reciprocal of the density, so we can actually get rid of those specific volumes and replace them by 1 over rho on each side. That gives us the statement that P divided by the quantity rho T must be the same for the inlet and exit. Okay, well now we're in good shape to solve for the exit pressure. You can just rearrange this to solve for P sub E. Make sure you don't misidentify rho sub E as P sub E. That's an easy misread, but you don't want to do that. Now we'll put in numbers. So we have all the values given. We take our ratios and we compute that P sub E is 730 kilopascals. Interesting. It wouldn't have been easy to predict whether the pressure was going to go up or go down as a result of flow going through this nozzle. We know that the density went up and the velocity went up, so the kinetic energy must be greater at the exit, but the temperature also decreased. In the near future, we'll apply conservation of energy laws to open systems to figure out how all of this stuff is interrelated.